Ladies and gentlemen, welcome to our new video. Today we will talk about Mlflow. So let's begin. Mlflow exists because machine learning work does not behave like traditional software. You rarely write something once and ship it. Instead, you run experiments, tweak parameters, change data, swap algorithms, and then try to remember what actually worked. Mlflow was created to bring order to that process. So here it gives you a single system to manage the full life cycle, starting from experimentation and going all the way to deployment without forcing you into a specific framework or platform. Okay, and notice the mission statement here. The key idea is unification. MLflow is not trying to replace TensorFlow, PyTorch, or scikit-learn. It sits above them. And why does that matter? Because teams rarely use just one library. Over time, tools change, but your experiments and models still need to be traceable and reproducible. MLflow focuses on fitting into existing workflows rather than locking you into a new one. And so, why do we even need something like this? Machine learning development is messy by nature. You might train the same model 10 times with slightly different parameters and get 10 different results. If those experiments live in spreadsheets or random notebooks, you lose context very quickly. That's where things break down. Reproducibility, versioning, and auditability become painful, especially when teams grow. So here, look at the comparison shown here. On the traditional side, experiments are tracked manually, environments are hard to recreate, and model lineage is unclear. The problem is not skill, it's process. Mlflow automates these overheads. It logs parameters, metrics, and artifacts automatically, standardizes model formats, and gives you a consistent deployment path. The goal is simple. Sorry. Less time managing chaos, more time improving models. Okay, look at that architecture. So, at the top you see three major capabilities working in parallel. MLflow tracking records, experiments, metrics, and parameters. MLflow projects defines how code runs in a reproducible environment. MLflow models handles how models are packaged in a consistent way. All of these feed into the model registry, which acts as the control center. And this is where models are versioned, promoted to staging or production, and linked back to the exact data, code, and parameters that created them. Okay, and under the hood, this splits cleanly into storage and serving. Look at that part. Metadata like parameters and metrics go into a backend store, often a relational database. Large objects like models and files go into an artifact store such as S3 or cloud storage. And deployment then pulls from these sources to serve models in production. This separation is intentional. It keeps the system flexible and scalable. Okay, and let's zoom out and look at the components one by one here. So tracking is your experiment memory. It answers questions like which run performed best and why. Projects define how experiments are executed so results are reproducible across machines. And models standardize um, how outputs are packaged so deployment doesn't depend on the training framework. The model registry coordinates collaboration by managing versions and states. The tracking server exposes everything through APIs, and the UI gives you visibility without digging through logs. Okay, everything is done. So now pay attention to capabilities highlighted here. Now, Mlflow is framework agnostic by design. Whether you use TensorFlow, PyTorch, or something else entirely, the workflow stays the same. Python is the primary interface, but REST APIs allow other languages to integrate. Maybe R, maybe Julia, maybe Java. Anyway, so storage is flexible. Environments are captured for reproducibility, and teams can collaborate through a centralized server. Deployment is equally flexible from local servers to Kubernetes or managed cloud services. Okay, and here some patterns. Look at that. What's happening here? Now, data scientists work locally, logging experiments to a centralized Mlflow server. That server persists metadata in a backend database and artifacts in cloud storage. Approved models move into the registry and from there into production deployment. The flow is linear, predictable, and auditable, which is exactly what organizations need, right? And adoption and integration here. Now, MLflow is used across finance, healthcare, e-commerce, and technology because the problems it solves are universal. Experiment tracking, reproducibility, and deployment do not depend on industry. The integration ecosystem reinforces this. So Mlflow works with training libraries, tuning tools, container platforms, and cloud providers. That's intentional. It acts as a connective tissue rather than a replacement. Okay, here we can see Mlflow integrations, right? Look at that. Anyway, let's continue. First page is okay and tracking. Now, this is usually where people feel the immediate payoff. Now, tracking is essentially the memory of your machine learning system. Every time you run training code, Mlflow can capture what you tried, how it performed, and what artifacts were produced. Without this, you are relying on notebooks, file names, or intuition, and that breaks very quickly. So, let's clarify the two core ideas first. A run is a single execution of your training code. One script execution, one run. Inside that run, Mlflow records parameters like hyperparameters, metrics like accuracy or loss, tags for metadata, and artifacts such as models or plots. An experiment is just a logical container that groups related runs together. But why does this distinction matter? Because you don't compare everything to everything. You usually compare variations of the same idea, and experiments give you that boundary. Okay, and now let's walk through the basic tracking example with Python here. Now we start by importing Mlflow and the scikit-learn integration. Look at that. So that scikit-learn module is important because it enables Mlflow to understand how models are saved and logged. Next, notice the call to Mlflow set experiment with the string iris classification here. And this line defines the experiment bucket where all upcoming runs will live. If it doesn't exist, Mlflow creates it automatically. And the data loading and training speeds are standard, as always, nothing special here. The Mlflow specific behaviors starts when they open a run. Now, this context manager defines the exact scope of a run. Everything logged inside this block is associated with one unique run ID. And inside the run, we define hyperparameters like n estimators at max depth. So these values control model complexity. And right after that, we explicitly log them using Mlflow log param. Why do this explicitly? Because later when you compare runs, you want to answer questions like which max depth led to higher accuracy. Looking parameters makes those comparisons trivial. And training here with random forest. This is standard scikit-learn code. Mlflow doesn't interfere here. It simply observes. After training, predictions are generated and metrics are calculated. And notice accuracy score and F1 score. These are scalar values summarizing model quality. And what can I say? As you know, we then log them using Mlflow log metric. Metrics are time series aware, which means Mlflow can store multiple values over time if needed, not just one final number. And that part, the trained model itself is logged. And this step packages the model and stores it as an artifact. That artifact is now versioned, reproducible, and deployable. You are no longer guessing which pickle file corresponds to which experiments. Okay, now auto logging. Now here writing log param and log metric everywhere get tedious, and Mlflow solves this with auto logging. Okay. So with one call, Mlflow can automatically capture parameters, metrics, artifacts, and even model signatures. This is framework-aware behavior. And here TensorFlow example for auto-logging. Yes, our libraries Mlflow, TensorFlow. Now, this single line activates auto-logging for TensorFlow. Okay, after that, when when the model is built, compiled, and trained, Mlflow automatically records optimizer settings, loss functions, metrics per epoch, and the final model. You don't write logging code for each piece. The training loop stays clean and tracking happens in the background. Okay, build model parts. And where's our training? And look at that. Pay attention. Here, each epoch produces metrics, and Mlflow logs them automatically. This gives you learning curves in the UI without any extra effort. It also captures the model input and output schema, known as a model signature, which becomes critical during deployment validation. And advanced tracking here. Look at that. Complex workflows often involve loops, cross-validation, or hyperparameter tuning. A flat list of runs is not enough here, and this is where nested runs come in. Okay, in the cross-validation example, we start with a parent run. Okay, and this parent represents the entire experiment. We log shared parameters like the number of faults and model type here. Then inside the loop, our faults, we create nested runs. Each fault becomes its own child run. Okay, and inside each nested run, the model is trained and evaluated on one fault. For example, look at gradient boosting classifier, fit and score, and fault-specific metrics like fault accuracy are logged at the child level. This preserves granularity. And you can inspect individual faults if something looks odd. And now, after the loop finishes, we aggregate results. NP mean, NP STD, and fault scores. These aggregated metrics are logged back to the parent run. This creates a clean hierarchy, one parent summarizing the experiment and children capturing detailed behavior. In the UI, this structure is immediately visible and easy to run about. Yes, okay, and let's continue by talking about artifacts because this is where Mlflow starts behaving like a real system of records. So, an artifact is any file that helps explain or reproduce a run. That includes trained models, plots, tables, and configuration files, even raw datasets if you want. The key idea is simple. If a file helps you understand a result, it belongs with the run that produced. So look at that. This example, artifact logging.py. We bring in Mlflow plotting utilities, pandas, and JSON handling. Inside the run context, the model is trained and predictions are generated. That part is intentionally abstracted away because artifact logging is independent of how the model is trained. Okay, and let me continue. Now, the first artifact logged here is a confusion matrix plot. We compute the confusion matrix, visualize it, save it to disk as a PNG file, and then explicitly call Mlflow log artifact with that file name. This step is important because Mlflow does not guess which files matter. You decide what should be preserved. And once logged, that image is stored alongside the run and viewable later without rerunning everything. Okay, and that's done. Tracking part. And okay, vlog feature importance. Write that. The model exposes feature importances, which we convert into a sorted table and save as a CSV file. Again, Mlflow log artifact uploads that CSV. This gives you structured, machine-readable insight into model behavior, not just a scalar metric. And configuration here, we capture the model type, all hyperparameters, the number of training samples, and the feature count. This is written to a JSON file and logged as an artifact. Why do this if parameters already logged? Think. Because parameters alone don't always tell the full story. The configuration file captures context in a way that's easy to audit and share. Now let's switch from local experimentation to collaboration and tracking server setup. Now, by default, Mlflow can run entirely on your local machine using the file system. That's great for individual work. But once multiple people are involved, you want a centralized tracking server with persistent storage. And compare the two setups shown here. Now in local mode, metadata and artifacts live on your machine and access a single user. In a remote setup, metadata goes into a database like PostgreSQL. Artifacts go into objects storage like S3, and multiple users can log runs concurrently. Same Mlflow API, different backend. Now look at that production configuration. Now let me align. Okay. The Mlflow server commands wires everything together. The backend store URI points to a PostgreSQL database, and The default artifact root points to an S3 bucket. The host and port expose the server to the network. This process turns Mlflow into a shared service. Okay, and on the client side, notice the call to Mlflow set tracking URI. This tells your training code where to send logs. From this point on, Mlflow param and Mlflow log metric behave exactly the same as before, but everything lands in the remote server. That separation is intentional. Your training code doesn't need to know anything about infrastructure. What is next? Okay, querying and comparing runs. Another comparison we can say, and logging is only useful if you can retrieve information programmatically. Mlflow provides APIs for exactly that. And in that example, we instantiate an Mlflow client. So we fetch an experiment by name and then search its runs. The filter string matrix accuracy greater than 0.95 acts like a query condition. So the order by clause sorts runs by accuracy in descending order, and max results limits the output. This gives you a ranked shortlist of strong candidates. And then we iterate over the runs and print their IDs, accuracy values, and parameters. This pattern is common in automation pipelines where decisions are made by code, not humans clicking in a UI. And here some uh, practices here. And you know, what can I say here? From that run, we construct a model URI using runs run ID model and load it directly. And this line is critical. It means the deployment code doesn't depend on file paths or naming conventions. It depends on tracked experiment results. And some things for practices. Now here, organize experiments. So comparisons make sense and use descriptive names and tags so runs are identifiable months later, and log everything that affects outcomes including defaults. These important, and time runs to code versions and datasets. The results can be reproduced. And clean up old experiments so signal doesn't get buried in noise, and use consistent metric names so comparisons are valid. Okay, that page is done. And projects. Now here it answers different question than tracking. Tracking asks what happened. Project asks how do I run this again somewhere else and get the same behavior. That's the motivation behind projects. They turn ad hoc scripts into reproducible executable units. Okay, now start with the big idea. A project is not a new framework and not a new way of writing ML code. It's a wrapper around code you already have. What it standardizes is how the code is executed. That includes which dependencies are installed, which parameters are exposed, and which command actually runs the logic. This is what makes experiments portable across machines, teammates, and environments. And look at that. There are three pieces working together. The ML project file is a contract. It declares metadata and entry points. The conda or requirements file defines the environment, so dependency versions are fixed. The source code contains the actual training or evaluation logic, and Mlflow doesn't care what's inside your scripts as long as this structure exists. And let's grant that with the concrete example, the project lives in a folder or Git repo. You see an ML project file at the root, a conda YAML for dependencies, Python scripts like trainpy and evaluatepy, and a data directory. This layout is intentional. Everything needed to run the projects lives together, which is what makes it shareable. And open the ML project file itself. The name is just an identifier. The conda environment line points Mlflow to the environment specification it should use when running this project. This means Mlflow can spin up an isolated environment automatically instead of relying on whatever happens to be installed on your machine. Okay, and here the most important part is the entry points. Okay, look at that. So an entry point is essentially a named command. Here main exposes parameters like training data, alpha and L1 ratio, each with a type and a default. These definitions are not documentation, they are executable interfaces. When you pass parameters later, Mlflow validates and injects them for you. Okay. By the way, here, notice how the command string works. Here, Mlflow replaces the placeholders with actual values at runtime. This decouples how parameters are passed from how the script is written. The same pattern appears in the evaluate enter point, which expects a model URI and test data path. That separation is what allows multi-step workflows. And we can look at conda, conda environment file. This file logs downtime down the runtime. Python version, channels, and packages are explicitly defined. When Mlflow runs the project, it creates this environment automatically. That's how you avoid the classic "it works on my machine" problem. Okay, and let's continue. Execution part. Now, a project can be run locally from a Git repository on a remote backend or inside Docker. The key idea is that the execution interface stays the same even when the infrastructure changes. Okay, now look at that. First command, running locally means Mlflow executes the project in the current directory, creates the environment if needed, and injects the parameters alpha and L1 ratio. The result is logged as a run automatically. And here now compare that with running from Git, and the only difference is the URI. Mlflow clones the repository, checks out the specified version, and runs the same entry point. This is huge for collaboration. You don't send code, you send a command. You can also target a specific entry point. This lets you reuse the same project for training, evaluation, pre-processing, or anything else you define. The project becomes a toolbox instead of a single script. Okay, and here, notice the experiment name option. This ties project execution directly into Mlflow tracking. Every project run is automatically tracked, which means projects and tracking are designed to work together, not separately. Okay, and projects can also be launched programmatically. Okay, and look at that part. This is how projects integrate into larger systems like schedulers or pipelines. The parameters dictionary replaces CLI flags, and experiment names are still expected. And here advanced project patterns, look at that part. Uh, Now, simple projects are fine for individual steps, but real ML systems are pipelines. That's where multi-step workflows come in. Look at the workflow script. We start a parent run that represents the entire pipeline. This run doesn't train a model itself. Its job is orchestration and traceability. And here entry points, look at that. This is a project run inside another run. Mlflow tracks it as a child run. Once it finishes, we query its outputs using the tracking API. And this is how data flows between steps without hard-coding paths. And let me continue here. Step 1 here, and step 2 does feature engineering the same way. Inputs come from the previous step's outputs, which are retrieved from tracked parameters. This makes the pipeline state explicit and inspectable. And step 3, model training. Here, the output here is a model artifact. We construct a model URI directly from the run ID, and that URI becomes the input to the evaluation step. At step 4, evaluates the model. At this point, the entire pipeline is fully tracked. Each step has its own run, and parent run ties everything together. And log pipeline level metadata. This information doesn't belong to any single step, so it's attached to the parent. When you open the